Learning with eyes. Okay, welcome to Ice Education, the only education that matters. So today, we are doing vibration, multiple degree of freedom. Just a quick recap. I do know that in diploma we did theory of machine. In diploma we did single degree of freedom. I'll try to write properly. Yeah, so that you guys can see this pen. Okay, in diploma what we guys did was single degree of freedom. And if you remember well, we were using a Newton law of motion, where we were saying that sum of all the external forces to be equal to mass times acceleration. And also, if the system was rotating, we used to say that sum of the moment about the pivot point of those forces should be equal to moment of inertia of the system multiplied by angular acceleration. I'm pretty sure you guys know about this. This is what we did in diploma. I know it's been a while, but do not worry about this, because in this topic we are doing multiple degrees. What we had in diploma, if I can just refer to this problem here, in diploma we had something like this. Let's say a spring, and then we have one mass here, k here, the constant what, and then they said derive the equation of the motion. It was simple. We could say that sum of the external force to be equal to mass times acceleration, and you know the story after that. Now, as you can see in this case here, we have mass 1 and mass 2. Because of the presence of these two masses, as you can see, x1 is moving in this direction, x2 is moving in this direction. Because we have two objects going in whatever direction, either it is the same or opposite, we are having multiple degree of freedom. I don't know if I'm making sense. How do you know that you have multiple degrees? You can just identify how many masses do you have in your system. That's where we talk about what? Multiple degree of freedom. So what you know here from diploma, you can literally forget about it, because we will be using the method called Lagrange's. Have you guys did Lagrange in Math 4? Lagrange's formula.
Yes. Yes.
So we'll be solving this problem now using Lagrange's. So what is the general formula of the Lagrange's that we will be using? I'm just gonna write it and you will see, guys. It is very, very, very easy. Here is the general formula. It says that derivative in terms of time of this basically met. There's no partial t. I will explain. Partial q dot I, like this, minus partial t partial q I plus partial u and partial q dot I plus partial r. I will explain. Partial let me erase. You will see, guys, it's very easy. It's very, very easy and straightforward. Partial qi, like this, to be equal to 0. Okay, it is equal to 0 because we don't have any external. What is an external force? Let's say under here you had a force pulling this thing down. Yeah, you equate this equation to be equal to that force. But in most of your cases, or 90% here in vibration of advanced diploma, will not include the external force. Now, what is happening here? How do you apply this formula? Like I said, the number of mass that you see on your problem tells you how many systems do you have. Now, you have to identify how many masses do you have. You've got two, m1 and m2. Now you have to solve for the differential equation of this system here using Lagrange's. Do you guys remember when you guys were doing energy method in diploma? You talked about kinetic energy and you talked about potential energy. Do you guys remember? If I can explain it to you, the T that you see on the formula here, T, it stands for kinetic energy. Are you with me, guys? U stand for potential energy. You will see it's very straightforward. Are you still with me, guys? Remember, I cannot see my screen on the other side. If you can just say your word so that I know that we're all together. Hello?
And we can see, guys.
Okay, no problem, my brother. I like it. Now, what is happening here, my guys? When you have this system here, the kinetic energy is caused by the masses. G is, I'm just gonna write a general formula. I'm pretty sure you guys remember in physics, kinetic energy, you guys used to write it like this. It is half mass times velocity square. If your system is rotating, you have a rotating system, the kinetic energy T is half moment of inertia of the system multiplied by the angular velocity square. So these are the T that you will always be having in this case here. Now, what is the first thing to do? We come to our system, we analyze how we having a linear or a angular system. What does angular means? Angular means a system that is rotating or turning. In this case here, guys, do you think that we have angular or linear? You can answer me, please. Just by the way you look at problem 1.
Linear.
Therefore, we do know that Benji wanted to talk. Why does Benji wanted to talk? Does he want to join the class? Okay, no problem. It's linear. So what do is we write T. We are here. We look at our system. We write T. We write all the kinetic energy that we see. Because we have two masses, we will write the two kinetic energy. So let's say for mass 1, I will write half m1 multiplied by x dot 1 square. In another word, if you don't know what is velocity in mathematics, we know that displacement is x, velocity is x dot, and acceleration is x dot dot. Because we are done writing like this, we are adult now. That's the simple reason why we write velocity with what? X dot. So this is the kinetic energy of the first mass. Plus, what is the other kinetic energy? It is half mass 2 displacement 2 square. Any question, my guys? All you have to do is to identify your masses and write the kinetic energy. Just what we did. You identify these masses and you write them. Is there any challenges there, my friend? Before we apply the Lagrange's formula. I guess we are good. Now, can we write the potential energy U? What is the formula of potential energy? The formula of U, it is simply half kx square. You know what is k? K is the spin constant. Now, how do we write the potential energy? Let's look at this figure here. We can see here K1 is only attached to the mass M1. is only having contact with M1. This one is just a support. So for that, U will be written like this: half K1 X1 square plus, now as you can see, K2 is between M1 and M2. So the potential energy formula of K2 will be written as half K2. Now there will be a change of displacement, final minus initial, or you can do initial minus final, it will give the same thing, but we're gonna keep it for consistency. We will go finals minus initial. So we'll go the displacement of x2 minus the displacement of x1. Why are we having this? Because K2 is between M1 and M2. That is the only reason why when you write the potential energy of K2, you have x2 minus x1 square. This is really important. If you can call this right, there is no way you can fail to use this function. Any question, guys, before we start applying the Lagrange's formula?
Can you please repeat why are we doing the x2 minus x1?
Okay, I'll repeat that, my friend. The only reason here, Mr. Cabello, because the spring K2 is attached between two masses. K2 is attached between M2 and M1, is holding them both. Let me just try to make a representation. This is what we have, like this. Let's say here it is mass 1. K1 is only attached to M1, as you can see here. Now, what is the scenario that we have? Basically, let me try to draw on top here, Mr. Cabela will erase it. You've got M here. You've got a spring here, and you've got another M here. This is K2, this is M1, and this is M2, my friend. Now, because K2 is holding these two, M1 and M2, the displacement between should be the change between the final displacement and the initial displacement, which is simply the displacement of x2 minus the displacement of x1. It is simple, Mr. Cabello. If I do this, just a simple example. If I have a mass here, oh wait. I have something in my mind. Let me write what's in my mind, just to make this clear. Okay, this is what I'm trying to do. I have this mass here, M1. I have this spring. I have this mass here, M2. I have this spring. I have this mass here, M3. Okay, let's say I'm here. I also have a spring and I have a support here. I call this one K1. I call this one K2. I call this one K3. Look what's happening. If I have to write the potential energy of K2 here, I will have half K2 displacement of x2 minus x1 square. If I have to write the potential energy, this one K3, sorry, this one K4. If I have to write the potential energy of K3 here, I will have half K3 displacement x3, which is displacement of mass 3, minus x2 square. Now, for the guy on top here, because it's being held by a support, is only having contact with one masses. So for K3, for K4 here, it will simply be half K4, the displacement of x3 square. So what I'm trying to say is, if your spring is holding two masses, therefore there should be a change of displacement between them. Did I answer you, Mr. Cabello?
Most definitely, yeah, I understand. No thanks.
Sure, my boss. Let me erase this and we can move. You see, I'll be doing this, and also, like I said, I want to do two examples. One will be angular, so that you can see what I'm saying when the system is angular, and I will put this on my YouTube channel, but you give me some time to edit them. I'll edit it tomorrow morning. Like I said, I want my content this time to be clean. Now, once you recall this, we can now apply the formula. What does this mean? I want to explain again something. Do you guys remember in mathematics, my brother? We had, let's say we have a function, we're calling it function of time. It was mostly function of time. They said ft is equal to t squared plus 2t plus 2. Just a random example. And they said, get the velocity. What do we do, my friend? We differentiate, right? If we differentiate this function, we get velocity, which is 2t plus 2. If we differentiate again, we get acceleration, which is 2. The same thing, I want to show you something. Let's say the same function. Now I put f of x to be x squared plus 2t, no, plus 2x, sorry, plus 2. Let's say I ask you to differentiate. What are you going to have, my guy? Are you going to have velocity? Or are you simply going to have first derivative of x, which will be 2x plus 2? Okay, there is something that I want to explain to you. When your variable is time, pay attention. When your variable is time, if you differentiate, automatically you are moving from one level to another. If this was displacement, you are moving from displacement to velocity. If you differentiate velocity to acceleration. But if you have a simple function, it simply means you are simply derivating. You'll get what I'm saying as we use Lagrange. So you must pay attention. The only reason why I'm saying that you have a variable of time in Lagrange here. This is very, very important. You need to know. Once I have time, it means I will be moving either from velocity to acceleration depending on what I have in my problem. I don't know if I'm making sense, but what I'm trying to say, if your variable is time, then you are moving between velocity, acceleration, or displacement velocity. But if your variable is just a function, you are simply differentiating. Let's apply the formula. If we have to lose Lagrange, you can say for mass 1 or m1, or I usually say x1 because m1 goes with displacement x1. Well, let's use Lagrange. This says partial t over partial qi. In this case, you will have partial t over partial. Where is there is a qi, you will substitute the qi by what? X1. That's what it means. This is just a general formula. So you will have then x1 dot. So what does this mean? We will come to the kinetic energy. I do remember in math, I think math 4, we did partial derivative. I hope you guys remember we did what is called partial derivative. When do we have partial derivative? When we have different variable. If you look at the kinetic energy here, this is the rule about partial derivative. If I'm differentiating in terms of x1 dot here, whoever which is not x1 dot is considered as constant. So in this case, let me use a different color. In this case, this whole expression here should be considered as a constant because the variable that we are working on is what? Is x1 dot. I hope I'm making sense. And we know differentiation of a constant is 0. We're good with that. Now, we are with this one. What is the differentiation of x1 dot? Guys, if you have 2x squared, what do you have? 2 will drop, you will have 4x. Simple here. If we differentiate this, we will have half multiplied by the 2 that will drop. So what will be remaining will be m1 x1 dot. So 2 will cancel 2. So definitely the answer that we'll be having will be m1 x1. dot 1. Let me put the dot clearly. Any question, guys? I feel like I'm going fast. Am I?
No, you're not. No questions. You're following.
Okay, that's nice, my brothers. And there's no sister yet, ne? In the class.
There is.
Oh, my brothers and sister, welcome, Sisi. What's your name?
Luyanda, yeah.
Oh, yeah. I will talk after the class. Yeah.
Okay.
Okay, we'll talk after the class. I don't want to say. I'll call you even.
Okay.
Yeah. Okay, the formula says that we have d in term of time of partial t partial x dot 1. This is just the formula. And remember what I said. I said if my variable is time, I no longer differentiate like this. It means I am moving now from what? If I have velocity, I'll be moving next to what? Acceleration. So basically, we are differentiating in time. If I can write what we are differentiating in time, in terms of time, is the expression m1 x1 dot. Which in this case, because the variable is time, this expression should change as m1 x1 dot. I hope you see the difference. In this case here, who's joining now? I'm already in the mood. I don't want my videos to be up and down like this. Who's joining now? Oh no, Swag, who's this? I don't know. Oh, I know my G. I know Mr. Owner Swag. So any question, guys? There's a reason why I insisted on this one. You can see when we did partial derivative, nothing changed on the dot here. Nothing changed here because there is no variable of time. But now, because time is the variable, we are basically moving from velocity to acceleration. I hope we are good here. So what we did, we basically did the first part of the formula for x1. We did this part. Now we have to move to this one, and to this one. Now, what is the other guy? The other guy will always be 0. You don't have to worry about it. I will explain. The other guy says rho t over is no longer dot. It's no longer dot on top here. You can see it's q I. So it basically mean rho t rho x 1. If you see here on the expression of the kinetic energy on top here, all you have are x dot. So you don't have to worry. It means there is no expression which is simply x1. Because there is no expression which is simply x1, it means the derivative here should be 0. Everything is taken as a constant. I don't know if I'm making sense. And in all cases, this guy here will always be 1. Will always be 0, sorry. I don't know why they include it there, but the person who made the formula decided to include it. So who am I to change it? Do you understand the reason why it's 0, guys? Hello?
Can you kindly repeat, sir?
Oh, yeah, I'll repeat. No, it's not sir, it's ice.
So,
No, it's fine. Okay, I was saying, if you look at the kinetic energy T, it says half, let's say m1 only, m1 x1 dot square. But here they say x1. That's what the formula says, x. There's no q dot here. There's only one dot in the formula, which is this one. The rest, they are the I don't know, let me erase, maybe it's getting someone confused here. The formula says q, this is q, I'm just writing I here. This is q, I'm just writing I here. This is q, I'm just writing I here. So you can, if you look at this, when you look at this expression, do you have x1? You don't have x1. You only have x dot 1. That's what I was saying. When it comes to this formula here, because all kinetic energy you'll be having will always have dot dot. So it means you don't have to bother yourself about this part here. It will always be 0. Because there is no expression in the kinetic energy that simply have x1 like this. Is it making sense?
Yes, it is. Thank you.
You are welcome. Hey, it's been a while they called me say. yeah. Okay, my guys. Okay, what we did, we completed the first. You're gonna see it's very easy. You will see. First one, second one, we move to the third one. The third one is rho u, rho qi. Remember the qi here, we replace it by this. This is what we replace in qi. Rho u, rho qi. Let's do it together. Joel left. I don't know what happened. Rho u, rho qi. The qi here is what? X1. So what do? We go to the expression of u here. We do the partial derivative where there is x1. But as we can see, if we look at here, my guy, you will notice that here you do have x1. Here also you do have x1. So both expressions will be part of this differentiation. Let's start with the first one. We are differentiating in terms of x1. Do you guys agree that we will be having half? The 2 will drop. As simple as that. Then we'll have k1 x1 only. It's basically you are having x squared. It is 2x. 2 drops. But here the 2 will drop. It will cancel this guy and this guy. That's what happened on the first one here. Simple derivative. Any question? Mr. Cabello?
No, I'm good. We can continue.
Sure, my G. Let's move. Now, there is something I want to show you. Do you guys remember the chain rule? You've done that in math too. Hey, there's a lot of math here. It's written u to the power n, with this n, u prime, u n minus 1. I will explain. Hey, this time, we still have 15 minutes. I will explain this before I send any new links. Now, what is happening here? Mr. Cabello, what's gonna happen here? You identify your u. I'm gonna do it step by step. Forget about half k2 for now. Let's focus on what's inside. You have x2 minus x1 square. Remember, we are doing integration. No, why am I saying integration? Differentiation by part where the variable is x1. Let's apply this formula. What is n? N is 2, so you drop the 2. What is u prime? U prime is the derivative of what is inside here. Remember, because the variable is x1, it means x2 is a constant. So differentiation of a constant is what? 0. We are only left with what? Minus x1. So what is differentiation of minus x1? It is simply minus 1. I hope I'm making sense. So that is our u prime that we did. Now we copy our u. Remember, u is the wall function, which is x2 minus x1. They said to the power n minus 1. If the power here was 2, n minus 1 should be 1. That's why the function remained the way it is. So if I want to write this with beauty, what we have here, I can say it is minus 2 multiplied by x2 minus x1. Any question on the chain rule? We just did some. I believe there is no question. So what does this mean? Here, if we have to bring the half, we're gonna have plus half. Remember, plus half. Let me write plus half. K2. Remember, this is the answer of the differentiation, which is minus 2 multiplied by x2 minus x1. You will notice that 2 will cancel 2. I'm going step by step so that we can be on the same line. 2 will cancel 2, so literally the expression here should be let me go k1 x1. It should be minus k2 multiplied by x2 minus x1. So if you want here, not if you want, we have to expand the x2 here. K1 x1 minus k2 x2. This will give plus k2 x1. Remember, minus times minus give plus. So this is what we do have. We have completed this one as well. So what is next? Next is rho r over rho, let me say x1 dot. Now, wait, let me ask you a question. Are you still with me? Mr. Cabello?
Yes, we are.
Oh. Nice. Now, there's something I wanted to say. Do you see the R here? It is called relay dissipation. When do you have a relay dissipation? You do have a relay dissipation when you have a damper in your system. So if you do not have a damper, don't bother yourself writing it. I hope I'm making sense. Let's say, for instance, there was a system like this. Instead of this guy only with a spring, they added a damper here. So a damper like this. Therefore, you can include the relay dissipation. We write it as R or D, it doesn't matter. It is written like this: half C x dot square. This is when you have relay dissipation. I will make sure I do an example with relay as well. But if you want to see on my YouTube channel, my very first video, I think it's the first or the second on this topic, there is an example with relay dissipation. You can have a look at it. But also here, I will make sure we cover something like this. So for now, don't worry about it. Because there's no damper in this problem, this guy here will not exist in the equation. I hope I was making sense. So now, how do you write your equation? Your final equation 1. So the relay dissipation here should be 0 because there's no damper. Now, how do we write our final equation? You just copy everything that you wrote. Remember, this one here was the final answer of this expression. So it's going to be, you just copy all your final answers. It's going to be m1 x1 dot dot. You copy this answer as well. Plus, what can I do here? I have x1 here and x1 here. I can make them subject of the formula. Do you agree? I will have k1 plus k2 multiplied by x1 minus k2 x2 to be equal to 0. So this is your equation 1 of this system. This is how you do it. Let me zoom a bit out. This is how you do it. You are simply applying some mathematics knowledge to get equation 1. So you will do the same for equation 2, and at the end you write them in matrix form. This is what we'll be doing next. Any question first, guys? Any question? This video will be nice edited when you see it on YouTube. Your voice will be there because I like it, but the shortcut or the what, you will not see it. I will take my time to create good things. Any question? Let me check thing. Okay guys, I just zoom out a bit. Let's say once you're done for M1, you can say it for M2 or X2. So we do the same thing, my good friend. We get partial T over partial X2 dot. Now what do? We can scroll up here and see where we are. We are still on the first kinetic equation formula here. But now, because our variable is x2, definitely we do know that, let me use a different, definitely we do know that the expression here where there is x1 will be 0. Why? Because we are differentiating partially and the variable is x2. On this expression here, there is no guy that has x2. It behaves like a constant. So we simply know that our only derivative is the guy here. So we can derivate it. If we have to do it, differentiate, we're going to have half. The 2 will drop. So what we'll be having is a repetition. You will see, you will be having m2 x dot of 2. So 2 cancel 2. The answer that you have is m2 x dot of 2. Now, what is next, Mr. Cabello? What is next is differentiating this expression in terms of time. So basically what you are having is you are differentiating in terms of time m2 x dot 2. Because the variable is time, now you are moving from a space of velocity to acceleration. That's why here you do have m2 x2 dot dot. It is very easy, guys. I do believe that this is the easiest chapter. In fact, vibration in all, there's nothing complicated. Any question, Yaya?
No questions asked.
Oh, do you understand me, Yaya?
I do.
Oh, Kalebu. I've learned some Sutu.
Ulebuhan.
Okay, my G. Yeah, we can do something before I send any new link. 2 minutes is a lot. A lot can happen in 2 minutes. Am I lying, Mr. Cabello?
You're not lying, man. You're not lying.
Yeah, you're thinking what you're thinking. Me.
Uh-uh.
A lot can happen in. Am I lying? Yeah. 2 minutes is a lot. Now.
I wouldn't know.
Ah. Okay. Yes, Mr. Cabello. After doing this, what do we do next? We move to the potential energy. So here we'll be having partial U, partial X. No, I think I'm skipping something, but I'm skipping it because I told you that it will always be 0. Do you guys remember? Partial T, partial this. Why is it 0? Because on your kinetic energy, you have expressions with dot. And this one here does not have a dot. That's the only reason why it is 0. But just for the sake of writing the formula, let's just write it. So let me just erase here and write what's supposed to be written. Let me use the board wisely. Let me use it full. Let me write here. Let me do it like this. It is partial T, partial x2, which is 0. So here, we'll have partial U, partial x2. So what do we do? To avoid going up and down, let me just rewrite that equation that we had. We had half k1 x1 square plus half k2 x2 minus x1 square. Okay, do we agree this is the potential for the potential equation? Now, if we have to differentiate this partially, do we all agree that this one will be 0? Because there's only one here. There's only x1. We are looking for what? x2. So in this case, the differentiation will only be applicable to this guy. Let's use the chain rule again. Let's write the half first here. Half k2. Let's do the chain rule. We drop the 2 according to the formula. 2. We go u prime. We differentiate what is inside. Because the variable is x2, so x1 should be a constant. So everything here is 0. So differentiation of x2 will simply be 1. We copy the function the way it is, which is x2 minus x1 n minus 1, which is 1. So you will see here 2 cancel this, so the answer that we have here will be k2 x2 minus x1. It's quite quick. I said a lot can happen in 2 minutes. So from here, the expression of this guy will be, if I can rewrite it, it will be k2 x2 minus x1. So we'll be having k2 x2 minus k2 x1. Remember, we do not have any relay dissipation. There is no damper, so we don't have to write it. So if we have to write the second equation here, it's going to be m2. Just expand this thing here. So what we have here, we're just writing the equation. Which answer is this one and this one? So we're going to have plus k2 x2 minus k2 x1 to be equal to 0. So this is equation 2. So usually you have to write this in matrix form. This just what we are doing is write the equation of the motion. We will do other things, normalizing and what, so I will also explain about it, but not now. Now what is happening here, I usually like recalling my equation. Equation 1, I can call it m1 x1 dot dot plus k1 plus k2 x1 minus k2 x2 to be equal to 0. So we do the same here. We write the second equation, which is m2 x dot dot of 2 plus k2 x2 minus k2 x1 to be equal to 0. So, and they will always ask you that to write this thing in a matrix form. How do we write it in a matrix form? Normally, these are the two equations. This is equation 1 and this is equation 2. You already solved for the equation using Lagrange's. But we are always being asked to write them in matrix form. How do we write them in matrix form? They are very easy. Let's do it together, you'll see. Let's do it together. This is what we have in matrix form. So the first guy you'll be having multiplying the matrix here will be x1 dot dot the acceleration and x2 dot dot. Okay, what do I mean by that? You do that in such a way that when you multiply, you have what you have in your previous equation. I know the English is too much, but let's see what I mean. Let me explain something first. Do you see where there is m1? M1 multiplies all these rows. I don't know if I'm making sense, but this is what I'm trying to say. Where there is 1, it will multiply like this. It will also multiply like this. Where there is 2, it will multiply like this, and it will also multiply like this. So if I'm making sense, x1 dot dot goes along this row, x2 dot dot goes along this row. You will see as we do it. Sometimes I have difficulty like now. I saw it in my mind, but my spirit was saying it another way. But you saw what I meant. Okay, what do I mean by that, Mr. Cabello? Let's do this. We want to write this in matrix form. We write it in matrix in such a way that when we multiply, we have what we had in the previous one. Let's look at equation 1. Do you guys agree that if I write m1 here, if I do x dot dot times n1, do you guys agree that it gives me the first expression here? Because I do have the first expression which is on this here, then that one is right. Now I come here. Do I have any expression that has x dot 1 1 here? No. Despite this guy here, no. Because of that, this guy here should be 0. Because when I do this times this, I found this. When I have this times this, I found 0. Because there is no other expression that goes with x dot dot 1. That's basically what we are doing. Now, when we come for x2 here, who is joining her? Tapiwe Mtetwa. Mr. Tetwa. You reminds me of this guy on Shaka Zulu, I think. Now, what is happening, my guys? Remember, everything that you read on top here, it has to make sense. Now, do we have any expression here that have x dot dot 2 on top here? No, we do not. Because of that, this should be 0. Do we have any expression that have x dot 2 here? M2 multiplied by this. Basically, it is this times this which gives you M2. Another thing that I want to tell you, whenever you are doing the matrices, if the values going like this are not the same, just know that you made a mistake somewhere in your equation. That's why it's good to do the matrix. Just know that somehow you failed, you made a mistake. You see as what I mean. Because we only have acceleration and displacement, so the next matrix here, plus, should be the displacement. Which in this case of the displacement, we have x1 and x2. Now, we do the same thing. When we look here, x1, what do we have? We have k1 plus k2 here. We have the expression that have x1 here. Do you understand what I'm doing, guys? Yeah.
Yes, I do.
Okay. So basically what's happening here, we're gonna have x1 multiplied by this. It will give what? K1 plus K2. You do it in such a way that when you multiply, you have what you have here. Now, what else do we have? Yeah. Do we have, okay, yeah, that's the, do we have any expression here? That's how we do it. Do we have any expression of K2 that has x1, of M2 that has x1, in such a way that when we multiply, we find what we have on top? Did I make a mistake somewhere? What is that, Yaya?
Is it negative K2 or just K2?
No, it is negative K2.
We must take it as a negative.
Yeah, this one.
Yes.
Mm-hmm.
Okay.
Thank you. Are you understanding me? I hope you understand me as well, Mr. Kabelo, Mr. Oshinze, Mr. Ntetwa, Mr. Lechiwe. Yeah, I'll get your name. Mr. Liklengo Nolo Ezekiel. Please tell your girlfriend to speak, my friend. Why is she quiet? Say hi. Okay, next thing is what, my guys? What we are doing here is we move again here. Do we have any expression of x2 on the first equation? We do have it, which is also minus k2. I hope you see it. So remember what I said. Once you are doing the matrices, if you don't have something like this the same in all type of question that we'll be doing here, just know you made a mistake in your equation somewhere. That's why it is important to do the matrix. It helps you even to track back if you find something different, just know that you are, I don't want to say you are fucking up, but you are making a mistake. Do we have an expression of x2 in the second equation here? It is positive k2, which is k2. So all the matrices here should be equal to the matrix of 0 and 0. So what we've done, we have solved for the first case using Lagrange's equation. Okay guys, how do I know that we have multiple degree of system? As you can see, we can identify the masses. You've got one masses here, you've got the other one here. So because you've got two, multiple start by 2. I hope it's just simple English. One is single. That's why when in the relationship they call you couple. If you guys are 3, you are multiple in the relationship. Even 2, you are multiple. I don't know what to say, but you get where I'm going. Okay, literally, what do we have here? Whatever this may be a disk or what, but for the look of things, how do you think, when you look at this, how do you think this object will go? This one here. How do you think? Look, it's under the ground here. What do you think it's going to do? It's going to roll, right? That's the reason even here they showed you an angle as this thing is rolling. Mr. Tabello, for the big screen. So in this case here, we have linear mixed with angular. I hope I'm making sense. So what's happening here? We're still using Lagranges. We're still using Lagranges. Now, what is happening? We recall the Lagrange's formula and we apply it. As you can see, guys, this is very, it's not difficult. Please go look at the previous video that I posted on my YouTube channel for last year. This one should be on YouTube, but not tonight, because I have to work on it. Anyway, in this case also there is no damper, so we don't have to worry about this. But like I say, I will look for an example where we have to include this. Now, what's happening here? I'm not saying this is not part of the equation. I'm just saying in this scenario there is no damper. So if there's no damper, there is no relay dissipation. It means no formula of this. We can identify the masses, my guys. We have, I will call this one M, just M. This one will be rotating, any object rotating. Let's start with the M1, my guy. With the M1, kinetic energy will be half mx dot square. X is the displacement here. Plus, because this object is rotating, it will be half moment of inertia of that object multiplied by angular velocity square. We are done. Easy as that, Mr. Cabello. Now, we move to U. U will be what? As we can see, the spring here is between these masses and this rolling object. I hope I'm making sense. Now, it's going to be half. I will just call it K because don't have any other constant again. Any other constant. Half K. The displacement final I will call X minus, let me say X theta. By X theta, I simply mean the displacement caused by this rolling object. That's what I'm trying to say. Square. Any question on how I wrote the kinetic energy and potential? Please talk to me.
Can you please explain the kinetic Again?
the kinetic energy. Thank you, my brother. Remember, do you agree that this mass is having a linear motion, my brother?
Yes.
Because of that, kinetic will be half mx dot square. Are you with me? Do you also agree that the second object here is rotating? That's the reason why it has an angle theta here. It's turning actually. It's rolling. Because
Okay, yes.
this... Sorry, my brother?
No, I understand.
Because it is rolling, it will have a angular motion. And when we have angular motion, the kinetic energy is written half moment of inertia of the object rotating multiplied by the angular velocity. That's why it is half j theta dot square.
Okay, no, I understand this.
Do you understand the potential too, my friend?
Yes, I got that one.
Now here's the thing. Do you guys remember in math? Hey, there's a lot of math here. You guys in math 1 did something like this. Sorry, my drawing is not good, but I want you to get the idea. You had something like this. I think you guys were calling this a sector. Or the arc length. Yeah, we call this arc length. Where this was S, this was your radius of your circle, and this was the angle theta. And we say that arc length, which is simply the displacement along this circle here through this angle, you guys said S is equal to r theta. So S, it is simply a displacement. So you can say X is equal to r theta. Basically, what does it mean? You can solve the displacement of a rotating object. That's the reason why I call this x theta. So in this our case, what is our x theta? Look, my friend, you have to pay attention. Let me zoom in. Yeah.
Yes, Ice.
Are you still with me?
Yes, I am.
I'm just zooming in. You can see where this object is attached here, and where okay, don't confuse the center of gravity of this object, which is simply the radius here, but they gave it to you for a reason. Now what I want you to see is this is the point where it's being pulled along. Let's say it was initially here, that's what they said, and it has moved through a certain displacement here. I don't know if you see it. It creates, let me use another color. It creates an arc length from here to here. That arc length is what I am calling x theta. So what is x theta? X theta will simply be r multiplied by theta. But you have to pay attention. What is r? R in this case is the distance, you can see, from this center to the bottom here, which is 250 plus 600. R in this case is not the radius of this thing. I hope I'm making sense. R is this distance completed from top to one of the corner of the circle. Am I making sense, guys? Mr. Cabello? Mr. Ezekiel, say something, my brother. Yeah.
You are making sense.
Oh, Kalebuwa.
Because we are like giving you thumbs up, but I don't think you can see them from your side.
Oh, I cannot see it because my screen is not showing your thumbs, though, Mr. Cabello. You can say something. My screen is only showing what I see here, not your face, not your thumb. Oh, God. You get what I'm trying to say. So, Mr. Cabello, the displacement here, x theta, if I have to write it for you here, x theta is simply going to be r theta. You know what is r? R is the distance from this corner to here, but that one you will see when it comes to substitute values, but I'm just giving you the whole idea. So what we have here, is going to be half now kx minus r theta square. So this is the displacement due to a rotating object. This is a displacement of a linear object. Key easy, my friend. Key easy. Now let's apply the formula. Let's say for x. Here you don't have to say x1 or what, because you only have one x. That if you do in real life, if you do have one. But if the system has a lot, some of us will have a lot of x to find. Now, Mr. Kabelo, are we together?
Yes.
Now, what we do here, we're going to have partial t, partial x dot. You don't have to say x1 or what, because there's only one x here. Now, you can see already that this one will be 0 because you don't have any x here. You don't have to worry about this. So in this case, you see it's a repetition. Still again, you'll have half, 2 will drop. We're going to have mx dot, so this would be mx dot dot. We good with that? Another thing is differentiating this function in terms of time, which is mx dot. The answer should be mx dot dot. So already we are done there. And again, remember what I said, we can come here and write rho t, rho x, which is 0. I have explained the reason just earlier on. You don't even have to bother yourself about it. So what is next, Mr. Kabelo? In this case, we need to solve for partial u, partial x. So this is our expression of the potential energy. Again, the chain rule, let's do it together once. We can still write the half k first. Let's do it. The 2 will drop, which always drop. We differentiate what is inside. Because x is the variable, so this r theta is a constant, it will be 0. So the answer of inside differentiation is simply 1. You write the function the way it is, which is x minus r theta n minus 1, which is r theta. So what does happen here, Mr. Kabelo? We will see that Su cancelled Su, so the answer that we have here will be k multiplied by x minus r theta, or kx minus kr theta. So once you have this, you can write your first equation. I want to do this fast. I hope I'm not fast. I believe that you guys are following. So the first equation is this guy plus this guy, and then this guy to be equal to 0. So this is equation 1. Equation 2, we do the same thing, Mr. Kabelo. We do the same thing, which in this case will be partial t, partial theta dot. Now, as you can see from this equation, on the kinetic energy, only one expression has theta, is this one. So this guy here will be 0 automatically without thinking much. So what we'll be having here will be half. The 2 will drop. So we're going to have j theta dot. So the answer here is j theta dot. So when we differentiate in terms of time, as you can see, this becomes like a game. We differentiate in terms of time, j theta dot. What we have is j theta dot dot. That one is fine, my brother. Now, what is next? You know the story. We also know that rho t of rho theta should be 0. I think we don't even have to write it now. Now we can go rho u, rho theta. Now, Mr. Kabelo, what do we do? Remember, this is the expression of u. Now, theta is the variable. Let's pay attention. Let's apply the chain rule. I can still write half k first. The 2 will drop, which always drop like I said. We differentiate what is inside. What is inside is x minus r theta. X is not one of the variable that we are differentiating because we are differentiating in terms of theta. So it means that for theta. So this is it. So it is half k. When we differentiate, the 2 will drop. Who's joining now? Okay, I am. The 2 drops. So what's happening here, guys? We differentiate what is inside because the variable is theta. X will be 0. So when we differentiate what is inside here, is like if you have 2x. What is the answer? It is 2. Here we have r theta because theta is the variable. R here is like a constant. So the answer should be what? R. But this one is minus r. That is the reason why when we differentiate here, we will have minus r. And we write the function that is inside like this. So what's going to happen? 2 will cancel 2. What we will be having will be minus kr multiplied by x minus r theta. So what is happening here? If we multiply inside, it's going to be minus krx plus kr square theta. So now if we have to write equation 2, equation 2 will be simply here j theta dot dot plus k r square theta minus k r x. So this one to be equal to 0. This is equation 2. So let's write it in terms of matrix form. So what are we going to have? Before writing it, I just prefer to recall both equations to see what I'm writing. So which is m x dot dot plus kx minus kr theta to be equal to 0. The second one is j theta dot dot plus k r square theta minus k r x to be equal to 0. Now let's write it in matrix form quickly so that we can go sleep. Now we have this matrix here in terms of x dot dot and theta dot dot. Let's apply what we are doing. Let's look at here at equation 1 here. Do we have any expression where we have x dot? Yes, which is m here. At equation 2 here, do we have any expression where we have x dot? No. So this should be 0. Now we check at equation 1 here. Do we have any expression that have dot dot? No. Because of that, this is 0. At equation 2, do we have any expression that's dot dot? Yes, it is j. That's why it is j. And this, remember I said, should be the same. Plus, open another matrix because we only have displacement. Remember the order goes acceleration, velocity, displacement. If we had an x dot here, we're going to do the matrix for acceleration, matrix for velocity, and then matrix for displacement. Because here we only have acceleration and displacement, that's why we are moving straight to displacement. I hope I'm making sense. So what we have here is simply x and theta to be equal to 0 and 0. There is no external force. Now, what is happening here? At equation 1, where there is k here, do we have any expression with x? Yes, which is k. Now, at expression 2, do you have any expression with x? Yes, it is minus kr. At equation at equation 2 here, do we have any expression with theta? Yeah.
Equation 2 or 1?
That's what I'm thinking. What did I say? Yeah?
You said equation 2.
No, here should be.
I was looking at the
yeah. At equation
it's
1,
negative.
do we have any expression with theta? Yes. Negative minus KR. Yes.
Yeah.
Now we get back here. At equation 2, do we have any expression with x?
KR squared.
Minus KR square, yeah. No, yeah.
It's positive.
No, look what I'm saying. At equation 2, do you see equation 2?
Yes.
Do we have any displacement with x? Look.
Any displacement with x?
Look,
Yes,
what happened
negative.
is x multiply like this. It also multiplies here. But
Yes.
remember, everything that you have down here is what you found on equation 2. Everything that you have on top here is what you find at 1. I hope I'm making sense. Hey Maya. Now, at equation 2 here, do we have any displacement with theta? Yes. Which is KR square. And remember what I said. These two expressions should be the same when you are doing this differential equation. If they are not, you are making a mistake.